Hi, so welcome to the fourth talk in this series of talks in honor of the start of the FC Kohli Center. So till now we have had three senior people, one each in computer science, maths and physics. But one of the things that we felt we should showcase during this series is also some of the younger people who have passed through CMI and who have done really well for themselves. So today is the first of the next generation who's going to speak in this series, and I'll ask Balaji to introduce him.
Okay, so it gives me special pleasure in introducing Ananth Shankar to give us a talk in this series called Perspectives in Mathematics in the FC Kohli inaugural session that we're having here. As Madhan said, it's an added pleasure that not only is he a rising star, but he's also from CMI. He graduated from CMI in 2012. He received his PhD from Harvard in 2017. And there he worked under the guidance of Mark Kisin. He finished his postdoctoral stint at MIT as the Moore Instructor in 2020, and then joined the faculty at the University of Wisconsin at Madison. He works in arithmetic algebraic geometry and has done really deep work already after his graduation. But what I want to specially mention is his recent preprint with Jonathan Pila and Jacob Zimmerman. This is settling the so-called Andre-Oort conjecture, and in its complete generality. This work, this preprint of his is already creating quite a wave, and we hope to see many more such great things coming from him. So it's a pleasure to introduce Ananth Shankar and have him call for this. I'm happy to give this talk today. Okay, Ananth, special points in moduli spaces.
First of all, thank you so much for inviting me. I'm really, really happy to be here, especially given that I've spent so many happy years at CMI. So everything I talk about is going to be joint work with Jonathan Pila and Jacob Zimmerman. So a lot of the objects that I'm eventually going to mention are they all sort of are generalizations of very fundamental objects, namely elliptic curves. So let me start off by talking about elliptic curves. So complex elliptic curve is just C mod lambda, where C is the complex numbers and lambda contained in C is a rank 2 lattice. So when I say lambda contains C is rank 2 lattice, what do I mean? I just mean that lambda is, so C is a field and therefore it's a group. You can add two complex numbers and so on and so forth. So a rank 2 lattice inside C is defined to be a discrete free abelian group of rank 2. So this means it's generated by two numbers, and it's generated by two complex numbers, and the two complex numbers have to be linearly independent as real vector space. Okay. Now, what are we doing? We're taking the complex numbers as a group and we're modding out by a lattice that's a subgroup. So the object that we're going to get is definitely going to be a group. The elliptic curve is it's a group, and not just is it a group, it's an abelian group because everything inside is abelian. And because we're modding out by a rank 2 lattice, it's also going to be a compact space. And it's a complex Lie group. Now, not just is it a complex analytic space, it also happens to have an algebraic structure. In other words, you can also realize it as solutions to complex polynomials. So when I say this, what I mean is given a complex elliptic curve C mod lambda, you can actually find complex numbers A and B, so that if you look at all solutions to the equation y squared equals x cubed plus ax plus b, that'll precisely look like your complex space C mod lambda. So the question that I first want to deal with is the following. So given lattices lambda 1 and lambda 2, when are the associated elliptic curves going to be isomorphic? So hopefully answering this question in a very suitable way will allow us to parameterize a set of all complex elliptic curves. So let's see how we answer this question of when two elliptic curves are going to be isomorphic. So one thing to note is that any map between, like, it's possible to use the theory of covering spaces and of free groups. It's not too difficult to see that any map between E1 and E2 is going to be induced by a map between the complex numbers. Any map little t is going to be induced by capital T, where your capital T is going to be a C-linear map. And of course, you just have a one-dimensional complex vector space mapping to a one-dimensional complex vector space. So any linear map between the two is just going to look like scalar multiplication. For some number alpha, for some complex number alpha. And the map little t is going to be an isomorphism precisely when capital T of lambda 1 is going to be equal to lambda 2. In other words, the first lattice scales to the second lattice under complex scaling. So in order to answer the question of when two elliptic curves are isomorphic, all you need to figure out is when your two different lattices are going to differ by complex scaling. So what we want to do is we want to classify lattices inside C up to complex scaling. Just for instance, by way of example, the lattice generated by 1 and I is going to differ by complex scaling by the lattice 2, 2i by just scaling by the number 2. Of course, you're also allowed to scale by other numbers, like non-real numbers as well, and you'll end up getting lattices that give you isomorphic elliptic curves. So let's go ahead and see when two lattices, let's go ahead and see how to classify lattices up to complex scaling. So all our lattices are free abelian groups of rank 2. So they're going to be generated, they can be thought of as integer combinations of two different complex numbers. So after scaling, you're allowed to assume that one of the two basis vectors is a number 1. And because the other number has to, along with 1, has to generate a discrete subgroup of C, you need the other number to not be real. So after scaling, you can always assume that one of your generators is 1 and your other generator is going to be a non-real complex number. All right. Now, by replacing your second generator by its negative if need be, you can also assume that its imaginary part is positive. So you can write it as x plus iy, where your imaginary part is strictly positive. So finally, we like asking the question of when 1 comma tau is going to scale to 1 comma tau prime by a complex number. And answering this question ends up just being the same as, solving linear equations with integer coefficients. And it's not hard to see that once you sort of write everything out, the lattice 1 comma tau can be scaled to the lattice 1 comma tau prime precisely when you can write tau prime as a fractional linear combination of 1 and tau. In other words, you can write tau prime as a tau plus b over c tau plus d, where a, b, c, d is a 2 by 2 matrix with integer entries having determinant 1. All right. So guided by all of this, let's define the upper half plane. H to be the set of all complex numbers with positive imaginary part. As it turns out, this so this is like a reasonably simple looking space, but it has a lot of extra structure. For instance, it has a natural hyperbolic metric. Given by dx dy over y squared. And you could look at the space of all holomorphic isomorphisms from the upper half plane to itself, which preserve this metric. So that's just called the space of holomorphic isometries. And that is going to be a group because you can always compose two such automorphisms with each other. And that group is going to be a very familiar group. It's just going to be the group SL2R. So SL2R acts on the upper half plane by holomorphic isometries. And how does it act? Exactly the same as this formula, except now A, B, C, D are allowed to be 2 by 2 matrices with real entries, not just integer entries. So the action is going to be tau maps to A tau plus B over C tau plus D, where now your matrix ABCD is allowed to be in SL2 of R. So just to recap, we have the upper half plane. We have like a rather large group, namely SL2R acts on it. And two different elements on the upper half plane. And you can think of lattices as parametrized by the upper half plane. And two different elements in the upper half plane give you the same lattice when they differ by an element of SL2Z, not SL2R, but SL2Z. So guided by all of this, let's define the complex modular curve. To be, it's called A1. It's just going to be the quotient of the action of the upper half plane by SL2 of Z. So orbits under this action parameterize isomorphism classes of lattices up to scaling is the point. So the action of SL2Z on the upper half plane has a really nice fundamental domain. And this fundamental domain was discovered by Gauss. Let me sort of try to draw this. So every point in the upper half plane is going to map to exactly one point in the shaded region under the action of SL2Z. So one way of thinking about, the parameter spaces of lattices up to scaling is just points in the shaded region. All right. So again, to recap, why did we do this? We did all of this because complex elliptic curves are in projection with lattices inside C up to scaling, which we just saw is in projection with the upper half plane modded out by SL2 of Z. So points of SL2, points of this quotient H mod SL2Z are in bijection with isomorphism classes of complex elliptic curves. So in other words, points of the complex modular curve are in bijection with isomorphism classes of elliptic curves. In fact, let me just say complex elliptic curves. Now, here's a cool thing. Just like elliptic curves are not just complex analytic spaces, they're also defined by algebraic equations. The same happens to be true about the complex modular curves. It's a very natural way to find polynomial. Well, there's a very natural way to sort of put an algebraic structure on A1. Namely, there are like very canonical polynomials whose vanishing locus is precisely can be thought of as the quotient H mod SL2Z. And not just that, the polynomials defining the modular curve actually, as opposed to having complex coefficients, have integer coefficients. None of this is obvious, but it happens to be true. And the wonderful thing is that just like complex points of the modular curve are in correspondence with isomorphism classes of elliptic curves, you could ask the same question over any ring. So given any ring, because the modular curve is defined by polynomials having integer coefficients, you could ask for solutions to these polynomials with entries in R. You could ask, like, given any ring R, you could ask for solutions to the polynomial equations defining A1 but like solutions in R as opposed to complex solutions. And by that's exactly what I mean by an R point of the modular curve. So the wonderful thing is that R points of the modular curve for any old ring are in bijection with isomorphism classes of elliptic curves over R for any ring R. So the last thing that I've said is not entirely true. There's like technicalities that prevent this from being exactly true. And these technicalities arise because the action of SL2Z on the upper half plane isn't a free action. Points have finite stabilizers. So this causes some amount of annoyance in this bijection being true. So let me put in quotes. But up to these stacky issues, this is pretty much true. So the takeaway is that A1 is the moduli space of elliptic curves of any base. So given any ring R, an R valued point of the modular curve is going to correspond to an isomorphism class of elliptic curves over that ring. Conversely, given any elliptic curve over that ring, there's going to be a unique R valued point of the modular curve. So the curve A1 parameterizes isomorphism classes of elliptic curves, and all of that is sort of, that's exactly what we mean when we say that A1 is a moduli space of elliptic curves over, any base. So we're not just going to be interested in elliptic curves and their moduli. These elliptic curves are groups and such like, they map to each other. So we're also going to be interested in maps from an elliptic curve to itself. Now, let me just remark that every an elliptic curve is an abelian group, and given any abelian group, there are very natural self maps on an abelian group that just make sense. Namely, fix your favorite number, let's say 3. And if you were to take an element x in an abelian group, you could map x to x plus x plus x. So because your group is abelian, this is actually going to be a homomorphism. So every abelian group admits these obvious homomorphisms to itself just given by scaling by an integer. So therefore, every elliptic curve also admits these obvious maps to itself given by scaling by any number. I'm going to sort of refer to these as obvious maps. And the question that I now want to talk about is what points of the modular curve have the property that the elliptic curves they parameterize, let's call it Ex, admits a non-obvious map to itself. So asking this is the same as asking for Ex to have an endomorphism. As it turns out, with kernel, a cyclic subgroup of size some number n bigger than 1. All right. So as it turns out, most elliptic curves don't have this property. Like, someone would stop you in the street and give you an elliptic curve over the complex numbers. It's overwhelmingly likely to not admit any maps to itself except for the obvious scaling maps. So the points parameterizing elliptic curves that do admit non-obvious maps to themselves are like somewhat special. And in fact, let's just define them to be special. And the elliptic curve, the associated elliptic curve is said to be CM. CM standing for complex multiplication. Now, as it turns out, this fundamental domain that I drew was due to Gauss. And Gauss cared about this because special points in this space actually parameterize more than just these special elliptic curves. They parameterize definite integral binary quadratic forms and also ideal classes of imaginary quadratic fields. So Gauss didn't care that very much about elliptic curves, but he cared very much about binary quadratic forms and ideal classes of imaginary quadratic fields. And that's why Gauss cared about this action, this fundamental domain. these points. These points also parameterize other interesting arithmetic data. So there's lots of reasons to care about them. So there's a very easy criterion for when a point is going to be special, at least in terms of what number in the upper half plane it has to be. So all you're asking for is when C mod lambda admits a map to itself. In other words, all you're asking for is, given a lattice lambda, can you find a complex number that scales that lattice to itself, not to something else, but actually to itself. Now, if you want to answer that question, it just boils down to solving easy equations. And if you solve them, you see that the point is going to be special precisely when, if you take any tau mapping to it, this tau has to satisfy a quadratic polynomial of the form a tau squared plus b tau plus c equal to 0, where a and b and c are co-prime integers. So not sort of working out why this is the case, but it's not too hard to see that this is the condition that tau has to satisfy for your elliptic curve to admit a non-obvious map to itself. All right. Now associated, and this a tau squared plus b tau plus c sort of looks like a quadratic equations and therefore like a binary quadratic form. And so associated to tau is a natural invariant called its discriminant. Discriminant of x is defined to be negative d, which is b squared minus 4ac, where a, b, and c are as above. That's why it's called the discriminant. So first of all, this already tells you that the number of special points is countable, because every special point has to satisfy a quadratic equation with integer coefficient, so it has to be in q bar. At least all the points in the upper half plane that are special have to be in q bar. That tells you that it's countable. Not just q bar, your coordinates have to be in an imaginary quadratic field. So that sort of tells you that most points are not going to be special. But that also tells you that there's infinitely many points that are special, because the set of all special points are dense in the upper half plane. So let lambda d denote the set of special points with discriminant d. Discriminant negative d. As it turns out, the size of lambda d is approximately d to the half, plus small error, up to small error. And this is a fantastic theorem by Brouwer and Ziegel, though maybe in this particular case it might have been due to work of other people. But the point is there are just finitely many, these special points, they sort of break up into finite clusters, countably many finite clusters, where each cluster is indexed by a positive integer d, and the size of the cluster is approximately d to the half. So this is another reason, this is another way to see that there's only countably many special points. Well, the question to ask is, how do these points get distributed in the modular curve? This question isn't hard to answer if you take every single d together simultaneously. But if you were just to take one specific, if you would take a sequence of d and analyze lambda d individually, well, then it's a lot less clear. And it's a fantastic theorem due to Duke that lambda d equidistributes in A1 of C as D goes to infinity. So loosely speaking, if you were to take an open set inside A1 of C, like, you can sort of compare its volume to the volume of all of A1 of C. Suppose, like, it has, say, the volume a third of A1 of C. Then as D goes to infinity, the number of points of lambda D that are contained in the open set is going to be approximately 1/3 of the total number of points in lambda of D. Exactly what I mean by equidistribute. And Duke proves this fantastic theorem about these points being equidistributed. So what I want to talk about is generalizations of, well, I want to talk about sort of, generalizations of the modular curve and also suitable generalizations of Duke's theorem to other contexts. Specifically, like, how special points are distributed, but algebraically. But in order to do that, let me first sort of, like, give a brief, say a few brief words about what generalizations of the modular curve look like.
So, sorry, Ananth, I have a question.
Yes,
so is it easy to produce such special points? As in, can I, because this would be an interesting question from a computer science point of view. There are many special points, you say. Can you produce me one canonical? I mean, is it easy algorithmically or whatever? I mean, I don't know.
Okay, so that's a fantastic question. And but the thing is, like, the question that you asked is extremely subtle, because there's like two ways of producing special points. One is in the upper half plane. And there it's not too bad, right? Just because you've got, you have to sort of pick your favorite imaginary quadratic field and look at any complex number which is actually lies in that imaginary quadratic field. So you have to sort of, okay, so yeah, so even that's not particularly easy, because given such a point, you sort of need to hit it by SL2Z until it comes into your fundamental domain. It'll still stay in the same imaginary quadratic field, but I mean, it's hard to predict where exactly it's going to land. I'm not sure if this is done algorithmically, but I suspect this might be doable.
Okay.
Something that's a lot more tricky is there's also an algebraic structure to the modular curve, and you could ask what the coordinates of your point are in those algebraic coordinates, specifically what the J invariants are of the CM elliptic curves. I'm not sure how algorithmically doable this is.
Okay.
But I think this question would be also super interesting, not just in the case of modular curves, but also in more generality.
Okay, thanks. Yeah.
Absolutely. Thanks so much for the question. All right. So what I want to now do is I want to sort of talk about generalization of the modular curve. And these are, beasts called Shimura varieties. So, well, one very important object needed to define the modular curve is the upper half plane. And generalizations of the upper half plane are so-called Hermitian symmetric domains. I'm not going to define what these are, but these are just complex analytic spaces which have natural Hermitian metrics. Well, the complex modular curve has a large group acting by holomorphic isometries, namely SL2R. Sorry, yeah, SL2R acts on the upper half plane by holomorphic isometries. Then the analog is just going to be the group of holomorphic isometries on X, and that's going to be a real Lie group. And this real Lie group is going to, of course, depend on X, but there's like, as you vary X, your real Lie group can sort of will vary across pretty much every most possible algebraic groups. All right. Now, SL2Z was extremely crucial in defining the modular curve. And the analog of SL2Z are so-called arithmetic subgroups of G of R. And the modular curve was defined to be H mod SL to Z. Similarly, the Shimura varieties are going to be X mod G of Z. Now, the modular curve is defined over Z. It's actually an algebraic space with whose defining equations have integer coefficients. And the same is going to be true for Shimura varieties as well. Except it's not quite Z. It's the coefficients defining a Shimura variety are going to be contained in extremely explicitly defined number fields, which can be determined once you have X and G and gamma. Not just that, in several cases, it's known that the equations defining these Shimura varieties are don't just have their coefficients in a number field, they actually have the coefficients in rings of integers. So this is, again, not entirely true, but it's directionally true. Well, your modular curve is a moduli space of elliptic curves. And your Shimura varieties, they sort of parameterize, they're like they carry what are called variations of Hodge structures. And well, the modular curve has certain special points which parameterize CM elliptic curves. At some points, not all points of the modular curve are equal, some points are more special. Similarly, Shimura varieties also have so-called special points. And these special points parameterize what are called Hodge structures with commutative Mumford-Tate group. Whatever this means. So I haven't yet defined what Shimura varieties are. I've just sort of told you how they relate to elliptic curves and what sort of data you need that generalizes the data that defines for you the modular curve. And I'm actually not going to define Shimura varieties because the definitions are quite unilluminating. Instead, let me give some examples of Shimura varieties. So the most fundamental example is the modular curve, and points of the modular curve parameterize elliptic curves. Now, elliptic curves are generalized by there are high dimensional generalizations of elliptic curves called abelian varieties. And well, these abelian varieties are also parameterized by really nice spaces, which happen to be Shimura varieties. And these beyond the elliptic curve are the most fundamental and basic examples of Shimura varieties. So the moduli space of polarized G-dimensional abelian varieties is a Shimura variety. It's called AG, and it's defined by not SL2, but a symplectic group. And special points parameterize CM abelian varieties. CM just means that your abelian varieties admit lots and lots of maps to themselves. Most abelian varieties don't. Well, if you were to, instead of looking at a symplectic group, if you were to look at an orthogonal group, where n is sufficiently small, then these correspond to so-called orthogonal Shimura varieties, which parameterize K3 surfaces, which are again objects that number theorists and algebraic geometers care about quite a bit. So a lot of the Shimura varieties end up parameterizing objects that algebraic geometers and number theorists care about. So they arise in moduli spaces of such objects. But not all Shimura varieties are known to do this. So these are like rather mysterious Shimura varieties These are called exceptional Shimura varieties. And these correspond to groups that are either exceptional Lie groups or certain weird types of orthogonal groups. But there's lots and lots of these weird Shimura varieties as well. Now, special points can also be thought of. Yes.
Can I interrupt you? What do you mean by associated to other groups? Can you just explain a little bit? I didn't understand that.
Oh, certainly. So these Hermitian symmetric spaces are actually constructed.
I see. Oh, so the G.
Absolutely.
The G. Okay, fine. Okay.
Exactly right. Exactly. The G that shows up. That's absolutely right. Great. Thanks very much for the question. So special points should also be thought of as Shimura varieties in their own right. But they're points, so they're zero-dimensional Shimura varieties. And given that your Shimura varieties are all defined over Q bar in number fields, your special points are also defined over Q bar. So there's only countably many of them. So most points are not special. Now the Shimura varieties also map to each other in various different ways. For example, if you were to look at the modular curve A1, which parameterizes elliptic curves, and the modular and the Shimura variety A2, the moduli space of abelian surfaces, is a very natural map. And here's how it's defined. Now, points of A1 correspond to elliptic curves. Now, given an elliptic curve, which is a one-dimensional group, how do you cook up a natural two-dimensional group? Well, you just look at E cross E. It's also going to be a group. It's not going to be two-dimensional. The association of E cross E to E gives you an association from points of A1 to points of A2. That is a map of Shimura varieties. Similarly, given a pair of elliptic curves, E1, E2, how do you get an abelian surface? Well, you look at E1 cross E2. And that's going to define for you a map from A1 cross A1 to A2. So there are several different maps. So like this, there are many maps between Shimura varieties. These are all defined group theoretically in terms of the groups defining Shimura varieties. And under all these maps, special points always map to special points. Okay, so I should say that these Shimura varieties are not just objects that sort of one is interested in just for their own sake. Studying Shimura varieties also tells you stuff about arithmetic. So let me just say in words that Noam Elkies proved his landmark theorem of elliptic curves having infinitely many supersingular primes by studying the modular curve. And you can also prove other very nice results about abelian varieties and about K3 surfaces and general about geometric objects you care about by studying these Shimura varieties. So if you want to understand certain objects, you can sort of understand them by studying their moduli. So that's another reason why Shimura variety is interesting, but I'm not going to go there for today. What I now want to talk about is the algebraic distribution of these special points in Shimura varieties. So here's what I mean when I say this. First of all, it's not too hard to see that special points are analytically dense in your Shimura variety. Just like one way to see this is in the case of the modular curve, you look at the upper half plane, the set of all points which have coordinates in an imaginary quadratic field, that's very clearly dense in the upper half plane. In fact, even if you were to fix an imaginary quadratic field, that's still going to be dense. Like Qi is dense in C. So this sort of generalizes to the case of all Shimura varieties, and it's not too hard to see the special points are analytically dense in your Shimura variety, let alone being Zariski dense. So here's a question that one can ask. So let S be a Shimura variety. when does an algebraic subvariety of your Shimura variety have a Zariski dense set of special points? Well, of course, S itself. Okay. Now, remember that Shimura varieties map to each other, and under these maps, special points map to special points. So let's define a Shimura subvariety of S to be the image of any map of a Shimura variety mapping to S. Well, because special points map to special points, and special points are dense in the domain, they're also going to be dense in the image. So any Shimura subvariety, yes.
And I'm sorry. Morphisms between groups induce morphisms between Shimura varieties acting on the same space kind of state. I mean, that's the kind of thing that you.
Great question. Not quite. So whenever you have morphisms between groups, that gives you morphisms between the Hermitian symmetric spaces. Like if you have a map between SL2 and SP4, you get a map between dissociated Hermitian symmetric spaces, and that descends to a map of Shimura varieties as well.
Okay, fine. Okay.
Great. Thanks very much. Right. So Shimura subvarieties of S also, just by construction, necessarily have a Zariski dense set of special points. Now, these are the so-called obvious ones, which are necessarily forced on you by how all these objects are defined. Question is, are there any other? And the conjecture of Andre and Oort is that no, the obvious ones are the only ones. So conjecture says that if you have any subvariety that has a Zariski dense set of special points, then, I'm sorry?
There's an arbitrary subvariety, is it?
Arbitrary subvariety. All I'm asking for is that it has a density of special points. Absolutely. So then Z actually has to be a Shimura subvariety. So the only ones that have a Zariski density of special points have to be the so-called obvious ones. That's what the Andre-Oort conjecture states.
So they're all images of other Shimura variety maps into this. That's what
exactly right. Exactly right. These are the only ones that can have a density of CM points.
It's like reconstructing the group in some sense. Is it natural to ask that? Is that what you mean by this?
That's a fantastic question. So if you knew, so the Andre-Oort conjecture would tell you that the monodromy of these subvarieties is going to be specifically constrained. Mm-hmm. And you can reconstruct the group by looking at what the monodromy is. Okay. But I don't think this is algorithmically easy or possible. Given a set of special points, it's not easy to say what the Zariski closure is. All you can say is it's going to be some Shimura subvariety. Okay. Great. So let me sort of illustrate this conjecture with an example. And in fact, this is one of my favorite examples. So let's look at the product of, let's take the ambient Shimura variety to be a product of two modular curves. It's a surface. Well, the only subvarieties of a surface, apart from points, are going to be curves. So suppose you had a curve sitting inside A1 cross A1, that's irreducible. And let's suppose that C has a dense set of CM points. That's the same as saying infinitely many CM points. Then the Andre-Oort conjecture predicts that either C is of the form a special point cross A1, like a point cross a product, a point cross A1, or obviously A1 cross a special point, or it's going to be Y naught of n sitting inside A1 cross A1 for some number n. Now, Y naught of n is a modular curve at level n. It parameterizes pairs of elliptic curves E comma E prime, which, so that is a homomorphism from E to E prime with kernel size, a cyclic subgroup of size n. Now, given this, there's a natural map from 1 out of n to a1 plus a1, namely, you take a point and you map it to E comma E prime. So 1 out of n sits naturally inside a1 plus a1. It does have a dense set of CM points, namely, you take a CM elliptic curve and anything isogenous to it, it's also going to be CM. But the point is, any curve sitting inside a1 plus a1 that has infinitely many special points has to be either this obvious one or this obvious one or this rather more interesting one. So the fact that you have infinitely many special points really, really pins down what your curve has to be. Now, another really nice consequence of the Andre-Oort conjecture, just for the Shimura variety AG, is that you can always find an abelian variety defined over Q bar of dimension bigger than or equal to 4 that's not isogenous to a Jacobian. This is a folklore question that people have been interested in for a long while. And the Andre-Oort conjecture for AG tells you that there are abelian varieties not isogenous to Jacobians over Q bar, which wasn't at all obvious until someone realized, until Chai and Oort realized that you can use Andre-Oort to prove this rather fantastic theorem. All right. So there's been a lot of amazing past work on the Andre-Oort conjecture. I'm not going to mention all of it. Let me just say that Eriksoven and Andre, not together, but like, separately, proved the Andre-Oort conjecture for the case of A1 cross A1. This particular case. So Eriksoven proved that every curve inside A1 cross A1 having infinitely many special points has to be one of these by assuming the Riemann hypothesis. Then Andre relaxed the assumption of the Riemann hypothesis. So this is like, one of the first results of the Andre-Oort conjecture. Then I think, Klingler and Yaffaev, they prove the Andre-Oort conjecture for all Shimura varieties, assuming the Riemann hypothesis. Then Jacob Zimmerman proved Andre-Oort unconditionally for AG, the moduli space of abelian varieties, and this also proves it for every Shimura variety that sits inside AG, just formally. And in recent work, Pila, Jacob, and I prove Andre-Oort for all Shimura varieties. All right. So I'm running. I'm sorry. Yes.
No, you have still time.
No, absolutely. So I think I have another 5 minutes left, and I'm going to talk about. I'll just say a few words about what goes into the proof of our theorem. So due to work of, I think, Binyamini, it suffices to prove, or rather suffices to establish upper bounds on heights of special points. So if you could take a Shimura variety, define a way height on it, and bound the heights of special points appropriately, then Binyamini proves that would imply Andre-Oort. Now these bounds were known for AG, and were an extremely crucial ingredient in Jacob's proof for AG. And they're known for AG due to, the average Kolmez conjecture being proved relatively recently. But like what happens in a Shimura variety doesn't embed inside AG. So what if a Shimura variety doesn't sit inside AG? The point is that your special points, they are zero-dimensional Shimura varieties in their own right. And very roughly speaking, you can sit them inside AG. So if you could construct a height on your Shimura variety so that the height restricted to your special points agrees with the height when your special points are thought of as subs of AG, then the bound from AG would give you what you want. So it suffices to construct heights on your Shimura variety which restrict to special points compatible with AG in a manner that's compatible with AG.
Is that an implication that special points of Shimura varieties always parameterize abelian varieties or something like that? I mean, what's
Absolutely. So like special points always parameterize what are called CM motives.
Mm-hmm.
So given any special point, you can tinker around with it a little bit. So it parameterizes, it also parameterizes abelian varieties. That's absolutely the takeaway, exactly. But the point is, we sort of don't want to just define these ad hoc points on ad hoc heights and special points. We need to define a height on the Shimura variety itself that restricts to these special points in a suitable way. That's the actual hard thing. Now, for AG, you construct heights given the fact. Okay, so the one thing that's sort of fundamental in defining heights in AG is the fact that AG parameterizes geometric objects. These geometric objects are used very crucially to define heights on AG. Now, these exceptional Shimura varieties, they aren't known to parameterize geometric objects. We don't even have a guess as to what geometric objects, if any, they parameterize. So, well, how do you define a height in the first place? Well, the thing is, your exceptional Shimura varieties, even though they don't have families of varieties, they have local systems which are defined group theoretically, which behave like the cohomology of families of varieties. And using the so-called p-adic Riemann-Hilbert correspondence at every prime p, what one can do is one can use these local systems to define a local p-adic height. And these do restrict well to special points. Now, here's the downside. Away from special points, it's a priori not possible to prove, well, it's a priori not easy to prove that these local p-adic heights glue well across primes to give you a global height on your Shimura variety.
Just a question.
Yes.
The height on AG is also coming from the associated dot structure or something like that, the way you're saying?
Exactly right. In fact, the way if you wanted to use abelian varieties to define heights in AG, that's exactly going to be the same height as, heights coming from the de Rham cohomology. That's absolutely right. Yeah, so these local heights, they needn't glue across, they sort of needn't glue to give you a good height on your entire Shimura variety. At least a priori. across primes P. Now here, so sort of a miracle happens. So what happens is there's this phenomenon called modular superrigidity that tells you that all local systems on these exceptional guys, and also a lot of classical Shimura varieties, but of course we just care about this for exceptional Shimura varieties, are so-called rigid. Rigid just means that you can't deform you sort of can't find positive dimensional families of local systems on your Shimura variety. And work of Eno and Grothendieck, which they very kindly generalized to the non-proper case in an appendix in our paper, tells you that rigid local systems are crystalline, which is a concept in relative p-adic Hodge theory, crystalline in the sense of Faltings, Fontaine, and Lafay. And this tells you that we're able to leverage this to tell you that the local p-adic heights are actually defined by global models of your local systems. And therefore they glue across primes. And this notion of crystallinity behaves very well under pullback, and so it's also compatible with AG. So these local heights that behave well at special points, we use work of Eno and Grothendieck to prove that they glue across primes to give you global height. And therefore we're able to bound, and therefore the compatibility with AG allows us to bound heights of special points, giving us the conjecture. All right, so let me stop here. Thank you very much for your attention.
Lovely.
Thanks a lot for a wonderful lecture. Any questions, comments?
I have a question, please.
Yes.
You use Margulis superrigidity. That applies only when the group of isometries is ranked greater than or equal to 2.
Absolutely, absolutely. So this doesn't apply to the modular curve, but it does apply to all these exceptional Shimura varieties.
Yeah, but it doesn't apply to products of modular curves, for instance.
That's absolutely right. It doesn't apply to products of modular curves. But these exceptional Shimura varieties, they all happen to have real rank at least 2, which is extremely crucial for us. Absolutely.
Any other questions?
May I ask a rather naive question? So,
Yes,
so in the special case of AG, is this a new proof, or is it back to Zimmermann's proof?
Okay, so that's a fantastic question. So the thing is, in the case of AG, we actually use the theorem for AG to prove our theorem. I mean, like, we very much need that these bounds are known for AG.
Oh, I see. Because this is only for the exceptional. Okay, okay.
Exactly right, exactly. We sort of use the fact that these heights that we construct are like compatible on special points with respect to AG, and we use the fact that the height bounds are known for AG.
Oh, okay, okay. Thanks. Yeah.
Absolutely.
Any more questions? Questions or comments? Okay. If you don't have any further questions, then we thank Ananth for a fantastic talk.
Fantastic. Really nice.
Thank you very much. Thank you so
You
much.
made it accessible to Marx.
Thanks very much.
Thank you very much.
Thanks, Ananth. See you.
Thanks, Anand.
Yeah, thank you so much.
Thanks so much. Yeah, thanks, Anand. Yeah. Take care.
Thanks, sir. Thanks very much for having me.
Yeah. Bye.
Bye-bye.
Okay.
You have bad cough, is it?
Sounds like
Oh, no, I just got my booster and yeah,
Oh, you're reacting to that. You're
I
reacting to that,
think
is
so.
it?
I think so. Yes, indeed.
Okay. Okay.
Yes.
it's not the revenge of the cat.
No. Cats are great.
Yeah.
Hi, Noop.
I don't know. All your classmates are there. Yeah.
Hi, Ananth. How is it going?
It's going well, Anup. Thanks very much.
Mhm.
How are things?
Things are okay. Long time.